Add it into it. Okay, so Chemistry 3101, this is where we left off last class, was discussing section 14.12, which deals with analyzing fragments. Remember that when you take an organic compound and you put it in a mass spectrometer, what's going to happen is you're going to hit that molecule with a high energy beam of electrons, which is going to knock an electron off of the molecule, which causes it to form a radical cation. And that's what we see right here. We have, this is just a molecule of pentane, and you see that one electron's been knocked off. It doesn't show you where that electron is, but what this is denoting in this yellow circle that I have here is that this is a radical cation, right? The radical is represented by the unpaired electron, and then of course the cation is represented by the positive charge. And what did we say last class? We said that a radical cation is unstable, okay, and then it's going to fall apart, okay, or in organic chemistry speak, it's going to fragment, okay, and it's going to break apart predictably. And I told you that's why mass spectrometry is such a powerful tool, because molecules will always break apart predictably. They're always going to break apart in a predictable fashion. And so the mass spectrum of an organic compound is like a fingerprint in a way. Anyhow, so let's say we have pentane. We subject it to that high energy beam of electrons. We make the radical cation. Okay, well, what's going to happen is it's going to fragment. And what are the fragments that could break off of this linear hydrocarbon? Well, we could break off, we could break it right here. Okay, we could lose a methyl radical. Remember that radicals are not going to be detected unless it's a radical cation. Remember that only charged fragments are going to be detected. So the only thing that we're going to see are what are in these green circles or boxes here, okay? Because it has to have a charge in order to be what's the word I'm looking for? Recognized or detected. Detected is the word I'm looking for. In order for it to be detected in the mass spectrum, it has to have a charge. And that's something that I went over with you in dirty detail. So if we calculate the mass of pentane, which is C5H12, so we take the mass of a carbon as being 12. So we have 12 times 5. And then we add 12 to it, we get a mass over charge of 72. So mass over charge is equal to 72. So what does that mean? If the mass over charge is 72 and I lose the methyl, which weighs 15, that means that I'm going to see a fragment at 57, right? It says up here mass minus 15, but what does this butyl cation actually weigh? It weighs 57, right? That's the mass over charge for this first fragment. What if it was to fragment here, right? It can fragment in a lot of different places. That means you'd lose an ethyl radical, which has a mass of 29. So if you take 72 and you subtract 29, what do you get? You get 43. So the mass of a propyl, right? The mass of the propyl cation weighs 43, right? We've lost 29, right? This thing here is the 29. This thing here is the 15. All right. The next one, if we lose the propyl, sorry. So this here has a mass of 43. And so our ethyl cation is going to have a mass of 29. So we could see a mass fragment at 29. And then if we lose all of this, right, if we lose the butyl radical, that has a mass of 57. And if you take 72 and you subtract 57, what are you left over with? You're left over with 15. So somebody's saying, what's the difference between this, right, and this? There's a big difference between that, right? The M minus 15 and the M minus 57, because it's what you see in the spectrum, right? Here you're losing a methyl radical. This is not going to be detected. All you're going to detect is the mass over charge of 57. This is a butyl radical. It will not be detected. What you're going to detect is what the methyl radical only, right? So there's a big difference between this fragment and this fragment. One's a butyl fragment and the other one is a methyl fragment. Does that make sense, Benjamin? Does that clear it up a little bit? Okay, right? They're two very different things. Remember, when you lose, like here we're losing the methyl radical, which is uncharged. Okay, it's not going to be detected over at all. Here you're losing the butyl radical. It's not going to be detected at all, right? Radicals are not going to be detected unless they're charged. If you lose 15, what do you have? You have 57 left over, right? You're going to detect 57, right? There's a difference between the number 57 and the number 15. Okay, so if you lose the butyl radical, then you see the charged methyl fragment, which has a mass over charge of 15. So these are common numbers. Only charged fragments are detected. Everything that's in the green boxes are the only things that are going to be detected. If something doesn't have a charge, okay, this doesn't have a charge, 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 they will not be detected under any circumstances, okay? If you go back in the slides, okay, to the introduction on mass spec, so if we go all the way back here, okay, we talk, it says the ions are detected, okay, only ions. Neutrally charged fragments are not detected. Okay, so the only thing we're ever going to detect is going to be an ion, nothing else. Anything's neutral, it will not be detected by the mass spectrometer. Okay, so let's go back here to those fragments. And these are good numbers to memorize. You know, they're handy to memorize 15, 29, 43, 57, right? Because we lose, you know, or we see methyl groups and ethyl groups and propyl groups and butyl groups all the time in organic chemistry. They're pretty ubiquitous, you know, so it's handy. You notice that they all have odd masses, right? From here, all you have to do is go from 15, you add 14, add 14, add 14, right? Over and over and over. Anyhow, kind of interesting there. And then I said, well, what if you had this molecule here? This isn't just a straight chain hydrocarbon, is it? Okay. Well, how is this molecule going to fragment? Now, it's going to fragment in a lot of ways. But what's being highlighted on this slide is the fragmentation right here, okay, where I have this red squiggle. That bond is going to break once you form the radical cation to produce a tertiary carbocation. Now, why are they highlighting this tertiary carbocation? Because as it says on the slide, all kinds of fragmentations are possible, right? That's why we see so many peaks in the mass spectrum, but we want to isolate or interpret the most important peaks, okay? All kinds of fragmentations are possible. If you're thinking, well, hey, Mr. Dion, couldn't it fragment here? Couldn't it fragment here? Yes, those can happen as well. But the reason why it's so important, this fragmentation, is because it produces a tertiary carbocation, right? It produces a carbocation that is so stable. So again, even if we were to run the mass spectrum on a molecule that we've never run before, it's going to fragment in a predictable way, right? We could predict that this molecule is going to fragment at this position. Why? Because it gives you such a stable carbocation, right? Because we know that tertiary is more stable than secondary, more stable than primary, and methyl. All right, since a tertiary carbocation, again, is more stable than a primary or a secondary or a methyl, the mass, the M-43 peak, is going to be the most abundant, right? Because this here, the propyl radical, has a mass of 43, right? This weighs 43. It doesn't have a mass over charge of 43. It just has a mass of 43. We don't say mass over charge because it has no charge. All right. There we go. So when we talk about alcohols, and this is what I was mentioning this morning before I started recording this lecture video. So if you weren't there for the class discussion, what I told you is that if you open up your textbook and you look at section 14.12, okay, and you read the section about alcohols, this is the sentence. I'll read it directly from the textbook. It says, the mass spectrum of an alcohol will typically not exhibit a molecular ion peak because alcohols readily undergo fragmentation in a mass spectrometer. So I didn't put that in my slides, but I'm going to add that here. We'll put here, typically do not see a molecular ion, okay, for an alcohol. And again, the reason why is just because alcohols are prone to fragmentation so fast. They just poof, blow apart. But they do have two main types of fragmentation. So even if you don't see the molecular ion, there are types of fragmentation that you can look for, right? And these are two that I covered yesterday. I covered alpha cleavage, and then I covered loss of water. Now, loss of water is a little simpler, right? Because loss of water, everybody knows the mass of water is 18. So if you see something that has an M-18, so if you know the mass of the alcohol, you subtract 18 and you see a peak, well, it's probably from the loss of water, right? Because water is 1 oxygen, 2 hydrogens, so that's 16 plus 2, 18. But alpha cleavage, now you look at this mechanism, and we haven't even studied these kind of curved arrows. Okay, these are what we call fishhook arrows. This is not covered until chapter 10. But I told you, you do not have to be able to draw this mechanism to understand alpha cleavage. Let me show you what it is. Okay, let me remind you. The carbon that the oxygen is connected to, here's the oxygen of your alcohol. The carbon that it's connected to, that's called the alpha carbon. That's why it's labeled with the Greek letter alpha. Any carbon attached to the alpha carbon is called a beta carbon. So if we label this as a beta carbon here, this one right here, okay, what you're going to see is that oftentimes an alcohol will break between the alpha and the beta carbon, okay? And you can see that this side is the side that has the charge, so that's the side that's going to be detected. And this side has no charge, so that side is going to be undetected. But that's what you're going to lose. So you can oftentimes predict or identify the ions that are a result of alpha cleavage, and we're going to look at an example of that this morning. So again, with an alcohol, typically don't see the molecular ion. Typically, that doesn't mean in every case, right? What does typically mean? It doesn't mean 100% of the time. It means a lot of the time. Okay. We also see alpha cleavage. I showed you how to identify that without drawing any mechanism. Okay, and then loss of water. Let me just say one more quick thing about alpha cleavage, which is mentioned here. The reason why alpha cleavage happens so much with alcohols, and it happens with amines, is because this is a radical cation right here. Right, you can see that there's an unpaired electron on the oxygen. That's the one of those electrons got knocked off, with the high energy beam of electrons. The reason why alpha cleavage is so common is because the fragment that you get is resonance stabilized. Right? There's always a reason why things happen in organic chemistry, right? My brother did a chemistry degree. He doesn't work in chemistry anymore. He works in the business world. And, he hasn't studied chemistry in 20 years, but he always has to admit, organic chemistry is logical. There usually is, there should be a logical reason for everything that happens in it. So kind of interesting stuff there. Well, an amine can also undergo alpha cleavage. Good news is that you don't have to draw this mechanism with these single barbed arrows. I'm never going to ask you to do that, not in Chemistry 3101. I won't, not until the very end of the class. But here's the nitrogen of our amine. The carbon that it's attached to, we call that the alpha carbon. Anything next to an alpha carbon is a beta carbon. So this is a beta carbon here, and this bond is prone to breaking. That's the bond that breaks during alpha cleavage. Why does it happen? Well, the reason why is just like with the alcohol, you end up with a fragment that is charged and it's resonance stabilized. So that's why alpha cleavage is so common in amines. The same reason is in alcohols. There's one more type of fragmentation that we look at in Chemistry 3101. We only see it with aldehydes or ketones. And if you look at the mechanism of what's called the McLafferty rearrangement, right? It's named after a person named McLafferty. You can see it's a pretty involved mechanism, right? It's quite a few arrows being pushed there. And again, I'm never going to ask you to push those arrows. And if you're like, well, if I didn't learn it, how am I going to be able to figure it out? Here's how you figure it out. Every science student all my students are good at recognizing patterns. So here's what you look for. You guys know a little bit of the Greek alphabet? Probably more than I do, right? You have alpha, beta, and you have gamma. And what comes after gamma is delta, right? So those are the lowercase, right? So I don't have the whole Greek alphabet memorized. Maybe if you were in a fraternity or a sorority or something, you might have it memorized. But the carbonyl carbon, okay, the carbons that are attached directly to a carbonyl carbon, those are called alpha carbons. So from there, you just follow the alphabet, alpha, beta, gamma. So in order for a McLafferty rearrangement to occur, you kind of got to have two things. You've got to have either an aldehyde or a ketone, and your gamma carbon, so I'll circle it in green, your gamma carbon must have at least one hydrogen on it, okay? So we could even write that in here. Gamma carbon must have a hydrogen. It can have more, it could have two, it could have three, but it's got to have at least one. And then I'm never going to ask you to draw the McLafferty rearrangement, but what makes the McLafferty rearrangement so unique and what makes it identifiable to a Chemistry 3101 student is this. Think about all these fragments that we've lost so far. You probably noticed that everything had an odd mass, right? 15, 29, 43, 57, okay? It's probably the only time besides water. Yes, I know 18 is an even number, but outside of loss of water, it's the only time we lose something that has an even mass. So if you calculate the mass of this, you'll see that it's an even mass, or it's an even number. Anyhow, so that's a giveaway that you've got a carbonyl. And if you're wondering, well, hold on, aren't carbonyls and carboxylic acids and esters and amides? They are. This is kind of an old-timey way of saying aldehydes and ketones. Sometimes chemists will call them carbonyls. And if you're like, come on, carboxylic acid, it has one too. You're absolutely right. But it's just, organic chemistry has a lot of old descriptors, I guess, that have just stuck around and I guess will be around here in 100 years from now. They just stick, or just stuck, I guess. And like, you remember when we were looking at nomenclature in chapter 4, and remember I showed you that some of the first organic compounds that were named were just, names pulled out of a hat. It's just the whimsy of the scientist who named it. She or he could name it whatever they wanted. They just picked names like barbituric acid. Anyhow, kind of morphine, right? It was named after the god of dreams. Anyhow, so that's what a carbonyl means. A carbonyl means an aldehyde or a ketone. This is something that I even teach in nursing chemistry. Okay, the whole idea of a carbonyl being an aldehyde or a ketone. So it's really important. Anyhow, so this is a summary of where we kind of ended up. Last lecture was talking about the different kinds of fragments, and I told you that if any of you are interested in doing a chemistry degree and taking an entire class devoted to mass spectrometry, which I did in my third or fourth, I guess my last year of university, in those kind of classes, you probably have to memorize, I don't know, maybe 100 different fragments, and if you're like, oh, you're bragging, you memorized 100. Well, I'm not bragging at all because it took me an entire semester to memorize them, And how did I learn them? Just by practicing. And so you're going to do the exact same thing. Right, you're going to have all of these concepts and fragments memorized. When you look at enough practice problems, they just kind of sink into your head after a while. 15 is a methyl, 29 is an ethyl, 43 is a propyl, so on and so forth. Right, McLafferty rearrangement. If you look for, some kind of even mass that's been lost, you'll say, hey, it's probably an aldehyde or a ketone. Right. Anyhow, there's all kinds of other fun ones that come up a lot in organic chemistry, or probably in the lab, if any of you are taking the lab with Mr. Geiger. Things like the phenyl radical. So if you have a radical cation, this has a mass over charge of 77. Another common one is a benzyl radical. So that would be this. So if you have a positive charge here in a radical, this has a mass over charge of 91. Anyhow, we could go on. There's some other cool ones like methoxy and stuff. And again, those are covered more in the lab. And again, I know some of you are taking the organic chemistry lab, so something to look forward to there, especially if you're the kind of student who really enjoys spectroscopy. I always have some students who are like, more spectroscopy, that was my favorite part of the class, And, if any of you are into puzzles, is anybody here into puzzles like Sudoku or things like that? I find that people who enjoy puzzles, and I'm not a puzzle maniac or anything, but I don't dislike them. But if you're the kind of person who enjoys puzzles, those people tend to like spectroscopy. Just, I don't know, something I've noticed over the years, people that like puzzles, because spectroscopy is kind of like putting a puzzle together. Anyhow, with that in mind, let's take a look at a practice problem. So it says, and this is kind of an interesting question. It just says identify two peaks that are expected to appear in the mass spectrum of 3-pentanol. So I'm going to help you out by drawing the molecule for you, because we haven't done alcohol nomenclature, but this is 3-pentanol, right? If you have the parent chain, this is pentane. And then when it's an alcohol, it ends in -ol. So it's an alcohol, like cholesterol. Cholesterol is an alcohol. Anyhow, and then the alcohol group, the hydroxyl, is at the third carbon. So this is 3-pentanol. Anyhow, that covers the nomenclature. Could anybody calculate the mass of pentanol and tell me, and we're talking about low-res mass spectrometry here, could anybody tell me what the mass of 3-pentanol would be? And it's not a trick question. You might grab your calculator and just, maybe you can do the mental math really quickly. The formula is C5H12O. So let's do it together. We've got 5 carbons. So we've got 5 times 12. we've got 12 hydrogens, so that's plus 1 times, or let's do it consistently here. Let's do 12 times 1. And then we've got 1 oxygen, so that's 16 times 1. We put all that spinach into our calculator. We get 60 plus 12 plus 16, so that's 72, plus 16 is 88. So we have a mass of 88. So if we were to have a molecular ion, right, if we were to convert this into a radical cation, the mass over charge of the molecular ion would be, or maybe I could write it like this. I'll keep it as simple as possible. The molecular ion mass over charge would be equal to 88, right? But what did we say with respect to alcohols? Would we expect to see a molecular ion? Would we expect to see that 88? We would not expect to see that, right? Because we know that alcohols typically fragment. So I have a question for my students. Could anybody tell me what types of fragmentation we might expect? What types of fragmentation might we expect for an alcohol? And it's not a trick question. Could anybody tell me what their favorite, type of fragmentation might be, or something that we might expect to see? So what were the two types of fragmentation that we saw earlier on, right? We said when we have an alcohol, yes, Jonathan, yes, absolutely. Right, we said with an alcohol, the two types of fragmentation, right? There's two main types of fragmentation for an alcohol. We could have alpha cleavage is one and loss of water is the other, okay? So those are the two main types that we can expect to see, alpha cleavage and loss of water. All right, so if we go back here to the question, right, even here you see loss of water from an alcohol, okay? Anyhow, so we have loss of water or alpha cleavage. So let's do loss of water first. So loss of water would look like what? How much does water weigh? What's the mass of water? Can anybody tell me? Yeah, it's 18. So if I take 88 and I subtract 18, I end up with 70. Therefore, I should see a peak at a mass over charge of 70. So that would be my first answer, is from a loss of water. The second thing would be alpha cleavage, right? I should see a peak due to alpha cleavage. So this is the first one. So we'll label this number 1. Number 2 would be alpha cleavage. And let's draw what would happen when we have alpha cleavage. So here's what happens. You take the alcohol. So let's draw the Lewis structure of the alcohol. Okay, OH, and we'll put in all the electrons here. So you see how there's 2 pairs of electrons on the hydroxyl? What happens when you hit it with the high energy beam of electrons is you're going to end up knocking off one of those electrons. Why would you knock off one of those instead of the ones in a bond? Because those ones are not participating in bonding. And so that is what's going to produce the radical cation like this. Okay. Now, see, I had the same thing drawn right here. Now, the carbon that is directly detached to the oxygen, that is the alpha carbon. That means that this is a beta carbon and this is a beta carbon. Now, hopefully you can see that there's a plane of symmetry running through the molecule here. So my alpha cleavage, it wouldn't matter if I drew the line here, if I drew the line here. Either way, I'm going to lose CH3, CH2, right? That's what I would lose, is I would have a loss. Where's my blue pen? There we go. Loss of CH3, CH2 radical, because I'm going to lose something that's uncharged. Could anybody tell me how much a methyl radical weighs? What's the mass of, sorry, did I say methyl when I meant ethyl? How much does the ethyl radical weigh? If we go back to the last table.
29.
Absolutely. Absolutely. So there we go. So now we've got 88, subtract 29. Okay. If you're going to go to medical school, you should be able to do 88, subtract 29, and that's going to give you 59. There you go. So therefore, we should see another fragment at a mass over charge of 59. And so these would be the two fragments that we would expect to see for 3-pentanol. What do you think? Not too bad. All right, those are the two most common types of fragmentation. Now, if you're wondering, like, hey, Mr. Dion, if I was to Google, you could try this. Google the mass spectrum of 3-pentanol. Go ahead and check it out. I guarantee you, you're going to see a lot more fragments than this and this, aren't you? You're going to see all kinds of fragments. You're going to see loss of a methyl. You're going to see, other types of fragments. You probably see a fragment at 29. Anyhow, you're going to see all kinds of stuff. But what am I saying? I'm saying when you see a mass spectrum, and we talked about this last class. Let's go back to a mass spectrum here. What was the one? I don't know. There's all kinds of them. Yeah. So if you look at a mass spectrum here, right? You see there's all kinds of peaks in here. I don't expect you to interpret every single peak. That would be not impossible. I'm sure a mass spectroscopist could take some time and maybe interpret every peak along the way. But I said, I want you to go for the low-hanging fruit, right? We said that pentane is going to lose 15. So if you take 72 and you subtract 15, what do you get? You get 57. Well, lo and behold, as Kelly pointed out earlier on, there is a peak at 57. Look at that, mass overcharge of 57 right here. We said the base peak was at 29, so that was from the loss, the base peak is at 43, so that was the loss of 29, so that was the loss of the ethyl. What if you lost a propyl? So that would mean that you would have a peak at 29. Lo and behold, there's a mass overcharge that's equal to 29. Here we have a mass overcharge of 15, so everything is exactly as we predicted. I just noticed I made a mistake here. This should actually say 72 minus. I guess it depends on how I was explaining this, but yeah, the mass overcharge is labeled correctly. Anyhow, you get the idea, okay? There we go. 70 and 59, would they be the most stable? So there's no, at 70, the ion is so small, I would say no. The one, and there's nothing at 59. Are you talking about a different problem? Oh, okay. Yeah, let's go back here. You're talking about the alcohol problem. Here. So, yeah, absolutely. The one from the alpha cleavage, I didn't really leave myself a lot of room here, but let's draw what we would end up with. So let me just move this a little bit here. Let me just move this out of the way. And again, I don't expect you to be able to draw these, the mechanism, the curved arrow mechanism for the alpha cleavage. But what it's going to look like is something like this. You end up with a radical coming in here, and then you end up forming a double bond there, and then you lose the ethyl radical. So you end up with the ethyl radical, but then you end up with something that looks like this, okay, where you have a lone pair here, like that, okay? And so that's going to be resonance stabilized. So yes, I would say that this would be the most stable of the fragments that we've identified because it's resonance stabilized, right? We can draw a resonance arrow here like this, and then we end up with something that looks like this, okay? We have this like that, and now we have a carbocation here. Yeah. So I would say the fragment from the alpha cleavage out of the two is definitely the most stable one that we've identified. But yeah, that's why alpha cleavage so readily occurs, is because it produces a stable fragment, something that is resonance stabilized. Well, I'll be honest with you. I have a note here in my notes, that says will not ask this. Now, what I would ask you guys to be able to do in this level, in this class that you are in with me, is I would ask you to be able to identify the fragments and where they came from, okay? What I would not ask you to do is I wouldn't ask you to draw this. Not in Chemistry 3101. That is something I usually cover in the lab when I teach it. I'll go over the mechanism in more detail, or I'll wait until we've covered, radical mechanisms, which again is covered in Chapter 10. All right? Anyhow, hopefully that clears up a little bit about fragmentation. Let's move on to the last section of chapter 14, which deals with degrees of unsaturation. So when you are faced with a mass spectroscopy or mass spectrometry problem, what I normally do is if I'm given a molecular formula of some sort, I'll do a couple of things. The first thing that your teacher, always does is I'll always apply the nitrogen rule first. Okay, can't help it. It's just the way I am. It's the first thing I'll always do is I'll look for the mass. You know, if there's a nitrogen, it's got an odd mass. You know, if there's an even mass, well, it's either got no nitrogens or it's got an even number of nitrogens. That's the first thing I always think about. But the second thing that I'll always think about is degrees of unsaturation. Sometimes we call the degrees of unsaturation, we call them U, okay? Sometimes it's called U, which just means unsaturation, or sometimes we call it the HDI. I like to call it the HDI, which stands for hydrogen. HDI stands for hydrogen deficiency index. Okay, the hydrogen deficiency index. And I'm going to explain to you what this means, degrees of unsaturation or hydrogen deficiency index, because what's the whole point behind mass spec? Mass spec is oftentimes used to help us determine the molecular formula of an organic compound, right? You have a big compound, what's its molecular formula? Okay, IR, what did we use that for? We use that to determine functional groups. Is it a ketone? Is it an aldehyde, right? Is it an amine? Is it a primary amine? Is it a secondary amine, right? Well, alkanes or saturated hydrocarbons, in case you never noticed, and we went over this before, they have this generic formula, right? For every carbon in a saturated alkane, you have 2N plus 2 hydrogens, right? If you go back to the pentane molecule, it has 5 carbons. If you take 5, multiply it by 2, you get 10. You add 2, you get 12, right? And I actually went over this with you when we covered alkenes. I asked you, you know, if you had 100 carbons, how many hydrogens would you have? And you guys were like, you know, 202. You knew it immediately, right? Because you just applied this formula. Well, what if we don't have enough hydrogens? What does that mean? What if we had C5H10, right? C5H10. What does that mean? It could mean a couple of things. It might mean that we have a double bond, right? If you had this molecule, that is C5H10. What if the double bond was here, right? That's also C5H10. Is there another way that I could have C5H10? Could anybody tell me, is there another way I could arrange those atoms? And it's not a trick. Cyclopentane, yes, absolutely. Right? Cyclopentane is another isomer. Right? Other ones would be just, you know, something that's branched like this, right? Anyhow, you get the idea. So C5H10 can have a bunch of different isomers. But when we have a double bond or a ring, we call that a unit of unsaturation, right? We've lost 2 hydrogens because of that. So a degree of unsaturation is a pi bond or a ring. It can be one or the other, okay? So what we're going to identify are the number of pi bonds or number of rings. For every degree of unsaturation, the number of hydrogens gets diminished by 2, right? Say, for example, you have C5H10, right, that we just looked at, right? I told you that it could also be a ring, right, because a ring counts as a unit of unsaturation. If you have C5H8, right, that means you went from 12 to 8, so you lost a total of 4. So that means you've got 2 degrees of unsaturation, right? So your HDI or your hydrogen deficiency index here is 1, right? Because you've only got 1 double bond. Here your HDI is equal to 2 because you've got 2 double bonds, right? You've got a triple bond. Anyhow, there you go. So those are unsaturated compounds. What if you had C4H6? Well, here you've got 2 degrees of unsaturation, right? Because if you had CnH2n plus 2, then C4 would be H10, right? So if you go from H10 to H6, you've lost 4 hydrogens. You lose 2 hydrogen for every unsaturation unit. So you have 2 degrees of unsaturation. So your HDI here is equal to 2. How can you have 2 units of unsaturation? You could either have 2 double bonds, you could have 1 triple bond, right? You could have a couple of rings, and then you could spice it up and have a ring and a double bond. Okay, so there's all kinds of isomers of C4H6, all right? So again, 1 degree of unsaturation, which we sometimes call U, and I'm not sure what Mr. Geiger uses. If you're taking the lab, he might use U, he might use HDI. They're both common, and they mean the exact same thing. I'll even write it here for you if you don't believe me. HDI is equal to U. They mean the exact same thing, okay? Every degree of unsaturation, again, is equal to 1 unit on that hydrogen deficiency index. So if you're wondering, you know, is there a formula that I could use to calculate this? The answer is absolutely there is, and I'll show it to you in a second. Anyhow, how do you treat a halogen if it's in a molecule, right? If you have chlorine, right, what's a halogen? The halogens are fluorine, chlorine, bromine, and iodine. They come up all the time in organic chemistry, especially once we get into chapter 7 and beyond. Well, a halogen in organic chemistry 1 is always going to be monovalent. It's always going to have just one bond. Now, what other atom always has one bond? Hydrogen. So you can treat a halogen on the HDI scale as if it were like a hydrogen. Okay? Treat it the exact same way. Right here we have C2H6. Here we have C2H5Cl, but you can treat it just like it's C2H6. Why? Because the chlorine is just like a hydrogen. Okay. If you have an oxygen, like in an alcohol or an ether, an oxygen doesn't do anything to an HDI. So here you have again C2H6 for ethane. Here you have C2H6O. When you're calculating the HDI here, you can just ignore the oxygen. Oxygen doesn't affect the hydrogen deficiency index at all. Nitrogen is kind of interesting though, because it increases the number of expected hydrogen atoms by 1. So again, ethane, as I told you twice already, C2H6, okay? Here we have C2H7N, right? 1, 2, 3, 4, 5, 6, 7. So when you have that nitrogen, it's like you can remove one hydrogen. So it's kind of like, it's like C2H6, right? You remove one hydrogen for every nitrogen atom that you have. Now, I'll be honest, I've taught this class a lot. I know that my students will usually gravitate towards this formula here. I've been teaching organic chemistry for a long time, and I still can't get used to the formula. Why? Because I don't use it, okay? I just calculate it in my head, you know, using all the tricks that I've learned over the years. But you know what? The formula is the best place for you to start. I will not give you this formula on the quiz. You must memorize this formula. So memorize formula, and I'll ask you to apply it, you know, on your next quiz for sure. It's 1/2 of 2 times the number of carbons plus 2 plus the number of nitrogens, subtract the number of hydrogens, subtract the number of halogens. Okay, so these are the halogens. I mean, everybody here is capable of nailing this formula, right? You can all add and subtract and multiply and divide, right? I know you can all do that. You're probably faster at it than I am. In fact, I'm pretty sure you probably all are. So, I mean, it's just a matter of putting the formula in your head. And again, it's like, and I know I keep saying this, but trust me, it's like a lot of the things in organic chemistry. Once you've done, you know, 10 practice problems with the formula, it kind of just gets stuck in your head, right? You have a hard time forgetting it. You know what? Every once in a while, and of course, we're not going to do this now because we're not doing paper quizzes, right? We do our quizzes as multiple choice, but you know, I'd have students who would take the quiz and they would just, you know, scribble down the formula as soon as the quiz started, just so they had it fresh in their head or something. But anyhow, that's the formula that you use. So HDI can be a very useful tool. How would it be so useful? Well, if I gave you a molecular formula of a compound and it had an HDI of 0, well, then you know it's got no rings, no double bonds, and no triple bonds, right? Just throw those things out. Okay. So let's give it a try. If I wanted to calculate the HDI or the U of these compounds, I'm going to use the formula. I'll scribble it up here. So you have HDI is equal to 1/2 2 times the number of carbons plus 2 plus the number of nitrogens, subtract the number of hydrogens, subtract the number of halogens, like that. So if we were to apply it to C6H10, right, we have 2 times 6, which is 12, plus 2, which is 14. There's no nitrogens. 14, then we subtract 10, which gives us 4. And then we take 1/2 of 4. What's 1/2 of 4? That means that our HDI will be equal to 2. All right. So I want my students to see if they can solve B and C and D and E. I'll give you a second to try them. If anybody can solve B, throw up the answer on the screen. And if you want to answer C, just write C and then type the answer in. Does anybody have the HDI for B? cha. All my students are right. The HDI is 1. See? Now that was a fast answer. Okay? Didn't take any of you long at all to figure that out. Figured it out super quick. What about C? I'll give it a few more seconds here. If you got the answer to C, just throw it up on the screen. Yep, absolutely. All my students are putting the exact same thing. They're all putting 2. Can I just pause with you guys for 1 second? You're all correct. You're all 100% correct. Can I just pause with you for a quick second? I know you probably are eager to just jump in and do them all really quickly. Can we just pause on this one for just 1 second? So to use the formula, you have 2 times 5. Okay, so it's 10 plus 2 is 12 plus 1. So, sorry, what am I doing wrong here? So that's 10 plus 2, which is 12, plus 1, which is 13. Sorry, 13 subtract 9 is 4. 4 divided by 2 is 2. Okay, so that's how you solved it, right? If you use the formula. Can I just show you quickly in my brain? So the parts of the formula are this right here. Okay, this is the formula. So 2 times the number of carbons, that's what C stands for. Then you just add the number of 2. You add however many nitrogens there are. Here you have 1 nitrogen. You subtract the number of hydrogens. Here there are 9 hydrogens. And then you subtract the number of halogens. Here there's 0 halogens. Does that help, Allison? Okay, good. All right. So and there's nothing wrong with using the formula. The formula is beautiful. It's why it's in the textbook. The way that I solve this in my head is this. The only thing I have that's of interest in here, because there's no oxygens, there's no halogens, there's no nothing. There's just a nitrogen. And I know that for every nitrogen, there's 1 extra hydrogen, right? So to me, it's like it's C5H8, right? So if I have C5, normally if it was saturated, it would be H12. So I take 12, I subtract 8, I get 4, I divide by 2, and then I know it's 2. So that's kind of the way that I do it in my mind, is just by memorizing the rules like that. Like if I was going to solve this one in my head, right, I ignore the oxygen. I know the chlorine is like a hydrogen, so this is like C3H6. C3, if it's saturated, would be H8. So 8 minus 6 is 2. 2 divided by 2 gives you 1. So the HDI here is 1. Okay, that's kind of how I do it. And again, you can do it however you want. And what you'll find is, again, and I know I'm repeating myself like an old man, but the more that you do it, the faster you get at it. But let's face it, it's not a race, is it? It's about getting the answer correct. Did anybody solve E? I'm sure somebody's gone ahead and solved E. Yeah, absolutely. Thanks, Jessica. Yep, absolutely. All of my students are correct. Yep. There you go. Perfect. Where did the 8 come from? So in this one here, okay, so since it's C5H9N, right, remember that for every nitrogen, you have an extra hydrogen, right? So it's like having C5H8, right? If you go back here with nitrogen, it increases the expected number of hydrogen atoms by 1. So you always have an extra hydrogen for every nitrogen. So I take this and I say it's like having C5H8. Now C5, if it's fully saturated, would be C5H12. So you take 12, subtract 8, which gives you 4. 4 over 2 gives you 2, like that. All right. Let me give you a crazy one, and I'm serious. This one's nutty. I'll give you a giant one and see if you can solve it. So what if you had something big like C17H19NO3? Can anybody solve that one? This one you'd probably want to use the formula, maybe. Yeah. Okay. Yeah. Absolutely, Warren. So Warren got 9. Yeah, all my students are getting 9. You're 100% correct, all of you. Yeah. Okay. So, how would you solve this one? You can solve it using the formula, or you could do it like this too. I'll show you my shortcut. Is I would say, well, oxygen doesn't change anything, so it's like having C17H19N. I've got one nitrogen, so it's like I have an extra hydrogen, so I have C17H18. Well, C17, 17 times 2 is 34, plus 2 gives me 36. So C17H36 means it would be completely saturated. So if I take 36 and I subtract 18, I get 18. I divide it by 2 and I get 9. Okay. Again, that's just kind of a shortcut. And if you want to use the formula, obviously it totally works, or it wouldn't be in the textbook, right? There's a good reason that he put it in there. All right. So you see, you can get all kinds of information from a molecular formula. Pretty cool, huh? So if we just, close our eyes, and you don't have to do that, but if you just think about what are the things that you learned in chapter 14, okay? What's the kind of cool stuff that you learned? Like, what were some of the take-home messages? You spent about 65% or 60% of the chapter covering IR. In an infrared spectroscopy, we talked about how you take infrared light, you shine it at an organic molecule, and you can get information about what? About functional groups. We learned how to identify an aldehyde, an amine, an ether, aromatic compounds, alkynes, alkenes, so on and so forth. So that's kind of cool. But if you think about it, if somebody gave you a molecule and said, you know what, you guys, if you could identify this molecule, I'll give you $1 million. You're like, sweet, thanks. That would be pretty great. And if somebody offered you a whole bunch of money to identify a molecule and you only had IR, would you be able to identify it? Probably not. I mean, you'd be able to identify functional groups. Is it a carboxylic acid? Okay, great. But there's thousands and thousands and thousands and thousands, probably millions of different carboxylic acids that are naturally occurring. So how would you know which one it is? Well, if you ran an MS on it, right? If you ran a mass spec on it and you identified the molecular ion, well, then at least you'd know the mass. So now you know a functional group, and now you know a mass. And if it's got an odd mass, hey, there's some nitrogen in it. You look for bromine, you look for presence of chlorine by looking at N+2 peaks, right? Remember that bromine, you have a 1-to-1, N+2. And with chlorine, you have about a third the height for the N+2. So we learned some cool stuff with MS. But you still wouldn't have enough information, would you, to be able to determine the complete structure of the compound? In the way that we were able to solve the problems and the problems that I'm going to ask you on the quiz or that are in the textbook is because they always give you more information, right? They always have to give you more information. So what I want to share with you is just one last thought. And this has got nothing to do with your quiz. This is just extra. This is extracurricular, okay? Later on, when we get to chapter 15, and I alluded to this at the very beginning of this chapter. Okay, if I get this thing out of the way, how do I do that? Oops, I didn't mean to do that. Okay, if we go right back to the beginning of this chapter, okay, I told you that in chapter 15, we're going to cover what's called NMR. And there we use radio waves. So we use bigger waves from the electromagnetic spectrum. But the point behind NMR, which we're going to cover later, is it tells you about the arrangement of all the carbon and hydrogen atoms. So it actually shows you how they're connected. And so before we ended the chapter, I always like to tell my students that IR and MS are tools that you need to help you identify the structure of an organic compound. So normally an organic chemist nowadays, she or he would use IR, MS, and NMR all together. So usually an organic chemist will use a bunch of different types of spectrometry and spectroscopy together, in conjunction in order to elucidate or determine the structure of an organic molecule.